Good morning, everyone. On behalf of this IEEE Vehicular Technology Society, UK and Ireland chapters, I welcome you to today's lectures. And this is basically a part of our 2025 series on AI, autonomy, and emerging trends in vehicular technology. I am Dr. Riazul.Islam. I'm based in University of Aberdeen, and I'm currently serving the chairs of IEEE VTS and UK Ireland chapters. And as usual, so I'll be moderating today's sessions. So as you have noted that this session is being recorded so that it can be shared with other members who are not able to join at the moment. And it is also good for others that we can share the knowledge in an open access manners. So I would like to acknowledge that our other VTS members, including our vice chairs, Dr. Tianjie and also Secretary Dr. Ashraf Mahmud from the University of West Scotland, for their supports to make these events possible. And it's definitely my great pleasures, my longtime collaborators and friends, to introduce this in this occasion, Dr. Nurilla Avazov. So he's Associate Professor of University of Inland Norway. So Dr. Nurilla does research in human activity recognitions, vehicular communication channel modeling, business innovations. He has contributed for forecastings and time series analysis in varying dynamic systems. Dr. Avazov also has research positions in many countries, including Norway, South Korea, New Zealand, and it is really great that he will be presenting today scalable AI-ready HAR datasets via multimodal motion captures and micro-Doppler simulation. And we kind of ask that if you have any questions, please hold it. So definitely we will have a follow-up question answer sessions. And with that, I am happy to give the floor over to Dr. Nurilla Avazov. So Dr. Nurilla, over to you, please.
Thank you very much for a nice presentation and introduction. So let me share my slide here. Can you see the slides?
Yes.
Yeah. Okay. Okay, thank you very much. And again, appreciate for this opportunity to present our recent research in the field of human activity recognition. And I'm very pleased to give this talk and share our recent findings. So today I'll mostly will be less technical. I will try to make it less technical and more visual illustrative to discuss in general, what are the human activity recognition and how we conduct the data and how we can realize and use those data in the field of AI. So first, the agenda is as follows. So I'll try to introduce about very generally what stands for human activity recognition. And of course, the objectives of today's talk will be highlighted to bring your attention what you are expecting from this talk. And then I'll briefly discuss about the HAR landscape and application needs. And then we start talking about sensing technologies used for HAR system. And the main core of the talk will be trajectory-driven simulation model for synthetic data generation will be presented, which follows up with the benchmarking, validation, and scalability in terms of various experiments in different environments. And then I'll sum up my talk and with highlighting some future directions using the proposed approach. So what is HAR? So many of us already are familiar with this term nowadays is when it's about recognition of various activities performed by the moving objects. And so the HAR stands for the process of identifying and classifying human actions using sensor data. So we collect various sensor data using different sensor technologies. So the core application, for example, could be a healthcare smart home, security, or human-computer interaction. For example, here we have a very brief scenario where we have a human activity recognition for identifying different activities performed by the person. For example, it can include simple walking, sit stand, or sleeping patterns, or if it is monitoring of the elderly people at home. So it's like what kind of activities they do by the routine, like eating, for example, toothbrushing, or in emergency situation, we can also be able to detect like scenarios where fall happens. So those are activities could be considered as a human activities to train, to build a robust, efficient AI models which can efficiently recognize those activities. And when we talk about, for example, more particularly in the healthcare field, so use cases are again about one of the things is most important to provide a timely healthcare to the person who had, for example, the fall activities to detecting their fault cases. Or there are other cases, for example, for the gait analysis or for rehabilitation. For example, they can do tracing and monitoring by observing the physical activities or certain physical physiotherapy exercises to by tracing the movement and the correctness of the movement and other activities. So for example, one of the thing, chronic condition observation or monitoring can also be considered as a healthcare and, for example, Parkinson's or stroke recovery scenarios. And another case, for instance, could be also considered sleep posture or breathing pattern analysis. Let's see this scenario, very brief and simple one, when we have intelligent health monitoring. So for instance, we start intake the patient digitally, where we have a digital profile, a specific patient or person, and then we try to monitor this patient during how they do actively during the day. So for example, how long they sit, how many steps they do daily, or if there is something emergency should happen. So we see those patterns from the log data. So the data will be logged in a person's or patient's personal profile. If there is something urgent happens, so recognition system will identify the pattern and it will immediately notify the healthcare service center, which the center will take the immediate and emergency actions by response. So for instance, sending the ambulance to the location of where this happens, okay? And the objective of today's talk is basically to address limitations of current human activity recognition datasets. For example, there are a lot of lack of diversity in terms of different persons, in terms of different gender, age, or body shapes, in terms of scalability, in terms of environments, and how realizable, how realistic those datasets. So, and we would like to also introduce a framework which allows to generate those scalable and if we allow to say AI-ready datasets using multimodal sensing approaches and simulate the realistic statistical data, which will be as close as possible to the real data. So we demonstrate the role of trajectory-driven simulation model, and we try to generate a synthetic data for replicating and augmenting real-world sensor outputs. So motivation is for this talk is a little bit explore the sensing technologies, such as the millimeter wave radar, which is RF, radio frequency-based sensing, and motion capture sensing like optical IMU-based sensings, which we will talk each of them in the coming slides, and also demonstrate analytical model and micro-Doppler signature analysis with respect to real data. And we introduced trajectory-driven simulation model for synthetic data generation, and we discuss the outputs with respect comparing to the real-world data and future direction. So, as we discussed, there are several HAR applications, and of course, each application requires a certain conditions. For example, we mentioned about healthcare scenario for detecting fall actions or rehabilitation monitoring, and this application requires high accuracy in terms of classifying accurately what kind of activities happened. Another scenario can be considered also as smart homes, activity-based automation, which needs low power continuous sensing. And we can also think about human-computer interaction for gesture control or augmented reality or virtual reality, which demands a fast recognition and refined recognition of the activities. And another very challenging and at the same time is a demanding domain is security for anomaly detection for surveillance, which requires the data must be robust to any occlusion or blockages of the signals. And sports and biomechanics, those are also considered for performance tracking, which also requires high resolution motion data. If we look to the scenario for smart homes and ambient intelligence, so in this case, use cases could be activity-based automation. For example, nowadays, many offices or places or smart homes, they are built or using lights by the sensor based, so or some other appliances will require to use those sensor-based activities. And in this case, energy optimization also based on occupancy or behavior. For instance, we can turn off the lights when there is no activity, there is no person, and at the same time turn on when the activity happens. And similarly, also for the tracking of any motions. And in this case, application requires a low power continuous sensing and context awareness where activity is linked to any location or time. So all the data will be logged and saved for the further future analysis. And in terms of scalability, it requires that it must work diverse home layouts and for the users. So that means if we build the system for smart homes and the AI-based activity recognition system should be very generalized and it can be adapted to any type of the person, regardless of the age, gender, and the body shapes. And also the application needs also requires a minimal user burden, so no frequent calibration or wearable compliance, which we'll discuss about this particularly in the upcoming slides. Okay. And another application could also be considered human-computer interaction, where the gesture recognition for touchless interfaces or augmented reality, virtual reality, motion tracking, or emotion-aware systems, for example, facial recognition or emotional recognition requires very high resolution sensing. For example, in terms of optical mockup or radar, if we consider is a very high frequency, should be considered to be able to detect those movements, very small movements in a precisely. And also this type of application requires low latency, which means real-time responsiveness. And so we need to process the upcoming data very short time, so to guarantee the on-time actions. And also we can now talk about sensing technologies used in HAR. So those can be considered as wearable sensors optical motion capture by short mocap systems, radar-based sensing, millimeter wave radars, for example, or RGB depth cameras, or RF Wi-Fi sensing, which is also part of the radar-based system, and audio and environmental sensors. And recent advances in these modalities have significantly improved accuracy, scalability, and adaptability of HAR across different real-world contexts. So if we look very briefly for each scenario and the sensors, for example, we can start looking into the wearable sensors, where we have inertial sensors, inertial measurement units, or IMU by short, could be placed in body parts to track the trajectories or to track the movement of a person. And then those signals will be afterwards sent to the computer for the future processing. So in this case, we will have recording the motion captures, and by using inertial sensors, and it requires wireless connectivity. If we need, we can also do real-time tracking for selectively body parts or for full body coverage. So in terms of this, it brings the flexibility for analyzing, investigating motion and movement of a particular body parts. And then by extracting the signals from this kind of system, we can build the skeleton and map to the particular actions or activities. Similarly, there is also optical sensors, optical motion captures, where they have used multiple camera setup, and these cameras will track the optical markers, which reflects the light, and it basically also provides very high resolution data, and with respect to IMU-based sensors. So in this today, we'll discuss both of these type of sensors, and then we'll address some limitations as well. And also there are biomechanical modeling, which is heavily based on calculations of the joints of each human body parts, which requires multidimensional movement rotations and also the relationship between different joints. So basically, this will start by building the skeleton, and it will also investigate the kinematics. It will require the domain knowledge in the system dynamics, motion analysis, and of course, it will require a lot of optimization in terms of building a human skeleton which performs specific activities. So then it will also require a lot of force analysis with respect to the ground, the speed, and other simulation models. So these are also one of the approach which allows us to generate human motion activity data. And so another model could be also considered as simulation models or software based animators, which allows us to animate and then at the same time generate motion data for considered scenarios and environments. For example, Unity is one of the very popular software which facilitates to generate various human characters to perform activities in different environments and scenarios. So as a sum up in terms of motion capture is basically the process of recording any movement in a given environment. And this system is used many different applications. For example, they are used in sports, in entertainment, and in medical applications, of course, virtual augmented realities and robotics. So as we have mentioned, optical mockup systems, there are various companies producing the camera-based setups. And for inertial or magnetic motion capture systems, There are Accentures, Rococo, Accents. Companies produce the various smart suits to produce the animation avatars, for example, and mechanical mockup systems, which are Gipsy, Sacros, and MetaMotions. So nowadays, also now software-based systems are in the market, and they are also producing quite realistic human animated motions. And now let's explore one of the IMU sensor-based mockup system, which is a Rococo Smart Suit. And this Rococo Smart Suit system uses 19 sensors, which have a 9 degree of freedom IMU motion trackers. And these motion trackers and sensors are embedded in the suit as shown here. For example, we have a main hub placed on the backside of the character, and all 19 IMUs, 19 sensors are connected to this hub, which will record all the data and to be sent to the computer. So in total, we have sensors in our hand, in the shoulders, arms, and in the head, and of course in the lower body parts, legs, foot, etc. So how this basically work? So basically we have a suit and then we have a person who wears the suit and performs a certain activity. So before performing activity, we have to make sure that the IMU sensor is calibrated correctly and it is electromagnetic field free, which means we at least should consider some meters of distance from any electromagnetic interference to reduce the distortion and to reduce the noises for improving the data quality. And full body motion capture in this case using 19 IMUs. And these 19 IMUs will be streamed in real time via Rococo Studio, which I will show in the next slide. And in this case, the person who wears the suit will perform activity, and those activity will produce the trajectories, X, Y, Z, for example. And this trajectory will be then sent to the computer via Wi-Fi router and for future analysis and processes. So how this system will work? So basically we have a Rococo Smart Suit Studio, which, for example, we start building our avatar, let's say, and then we start calibrating our avatar in a standstill position. After calibration has been done, then we can start performing activities. So we can see here, we can visualize our avatar from different views, from the front, top, left, right, back. So for better visibility, for better positioning. And then we can have different intacs here. So where we have a different scenarios. So we can capture multiple scenarios for those particular activities. And then we can also see our avatar in terms of a skeleton representation. Finally, when all the sensors are well calibrated, so we can see in this plot where the IMU sensors are green light, that means connection established well and there is no loss in terms of data. And once the data has been recorded, so we can then extract in different formats, for example, FBX, BVH, CSV, and C3D formats. And each format has a different information may contain. So it can contain trajectories, forces, and other relevant human action data. And we can also set the frame per second, how many frames we want to explore. So these are basically how we can record the activities for this Rococo Smart Suite by using the studio. So all recorded data will be saved as here as follows. And then we can download export the all relevant data. So before looking into mockup data, we will also see when we explore our exported data, we will see the recorded trajectories for the human body parts, such as head. For example, we can also get the data for the shoulder, for the upper arm, lower arm, hands, and then the upper legs, lower legs, and feet. And of course, we can also have a smart gloves, which will be corresponding, which will produce the data corresponding to the finger motions. So this is very briefly information about our mockup system using Rococo Studio and Rococo Smart Suite. Now let's explore what is the optical motion capture system and what is this. So in this case, as an example, I will explore the Qualisys motion capture system. Here we see the environment where we have the cameras which can be placed in a circular way around the person who will perform activities. And here we have a MICU's cameras, very high resolution cameras, and these cameras are tracing the markers placed on the human suit. And then we will have a calibration kit, which I will explain the process and the role of this calibration kit. So as you see, we have here indoor environment, and the cameras are placed around the target and the person. And here in the middle picture, you can see the video recording range. So for example, on the left side, we see the cameras placed in the almost similar elevated with the person, but on the center picture, we can see the cameras could also be placed on the ceiling of the environment. And in this case, we have to calibrate well, so when the person does activities, so all the area will be performed. And then finally, after obtaining the data, we can capture all the motion data and then build the skeleton with respect to the activities. So here you can see how the calibration has been performed. So all these transparent blocks corresponds to the movement of this calibration kit. So this triangular shape defines our origin position, and this kit with the T shape, it will basically create a volume where the person will perform activities. For example, if we consider walking activities, so we have to make sure that this kit has been done, which covers all those distances where the activities and experiment will be performed. Once we make sure that this calibration has been done, and then we can start performing activities and recording the trajectories. So here we can see how we can record the trajectories with respect to different cameras. So here we have 1, 2, 3, 6 cameras, and it is recording the person's movement. Each trajectory, each line corresponds to the markers. So let's say we have 20 or 19 markers. So each line will respectively track and produce the trajectories in the Cartesian coordinates, X, Y, Z, which we will use them later on in our simulation model to produce the human motion data. So, and if you pay attention, we can also select the data for the particular human body parts. So this is in the experiment setup where we have our person wearing the suit. This suit is a Rococo suit, so that means we can record at the same time IMU-based data and optic motion capture data obtaining from the markers. And here in the center figure, you can see that we have placed our radar kit, which I will explain in the next slide. Our radar will send the signal, and then we'll capture full 3 modality sensing for these kind of activities. And we have cameras for capturing the movement of the markers, and radar will record the real signals. So how we record, how we conduct the data for the quality mockup system. So we basically, after calibrating, we built our avatar, we built our skeleton, and then in this figure where you see B, we have a markers placement. So we also requires data processing, data preparation. Sometimes some markers corresponding to the right or left will be displaced or will be switched. So we have to label them manually correct afterwards. So it will take some time also to process the data and data preparation. So here we can see very brief block diagram for calibration, marker identification, and skeleton for the avatar. See, after camera calibrated, so we capture our signal and then we produce 2-dimensional marker identification. So as I said, we will, for correctly reconstructing our full avatar, we have to identify markers and label them correctly, because after extracting the trajectories, we will make sure that all trajectories extracted correctly for building correct data. So this is data cleaning process. So we calibrate data, we extract the trajectories, and then we use these trajectories to compute, for example, Euclidean distances, or then compute the propagation delays and micro-Doppler signatures we will discuss in the coming slides soon. Okay, so far we have addressed the motion capture-based sensing. Now I'll talk about millimeter wave radar-based sensing. And in this case, what is radio frequency-based HAR systems? So they basically demonstrate several advantages. We don't need to wear any kind of sensors, no user involvement in the system, because we don't have to worry about, do we need to charge the system? Do we need to take care of its functionality, etc. And good coverage in indoor environments. Let's say in the dark, when visibility is not in place, so radio frequency will work fine. And in RF-based HAR systems, usually transmitter sends the signal in indoor environment, while the receiver collects the waves, carrying fingerprints from the moving objects. So in this case, to extract those fingerprints is quite important and vital to understand the nature of underlying wireless channel, which corresponds to what kind of activities, movement happen in the environment. So the interest in investigating RF-based techniques comes from the technologies as a privacy preservation or safety. For example, radars systems are based on analysis of propagation delays, signals, and then Doppler frequencies of the received signal. And if we look to the millimeter wave sensors, which have significantly progressed in the HAR, in IoT systems, or even in the 6G communications. So in this regard, accurate channel model provides insights into how millimeter wave signals travel and reflect and scatter or obstructed in different environments. So in this regard, environment is also crucially important to consider. And indoors, millimeter wave signals face usually obstruction, non-line of sight scenarios, or disrupting signal connection, and these necessitating the innovative solutions. So for example, backscatter technology, right? Or sensing and integrated within the communication is important. And therefore, importance of channel models will be in place where radar systems or radio frequency-based systems working with the certain operating settings and antenna setups are plays a key role in building and generating human activity recognition datasets. And in this regard, considering various environment settings and personality and activities will require to prepare, to set up, and to generate a reliable, accurate, and efficient data set for the human activity recognition. And in millimeter wave radar-based sensing, there are several principles. So we have to measure the range. We need to measure the velocity, angle, for example, and then there is a scenario could be considered like an area with the open space or an indoor with a certain geometrical representation. Here in the picture, you can see that the person performs the moving activity in front of radars. And here we have a radar kit produced by Ankortech. And here we have a 2 transmitter and 4 receiver antenna connections, as you see. And antennas basically sense, in this case, the signal to the person, and the scattered signal will be received at the receiver antenna. And then we can save the data, record the data, and then we produce the statistical characteristics of such a signal for analyzing and labeling the performed activities. As you see here in the picture, the person also wears a smart suit, where in here you can see the Wi-Fi radar, and at the same time we are recording motion capture system produced by the IMU sensors, and we are capturing the motion by using real millimeter wave radar data. So how system basically works. So here, for example, we can establish our antennas. Let's say if we consider multiple input, multiple output scenarios, so we may have multiple antenna system in a certain position to track and to produce more generalized data set. So which we can say visibility independent, right? So we can then be able to generate more accurate data, which can represent the images and the snapshots of those certain activities. And then we'll use to process the data as a software-defined firmware for the radars for capturing the radar signals. So these are basically the different sensing technologies, and now we'll talk about our trajectory-driven simulation model. And in this case, so we have trajectories obtained from the IMUs, right? And these trajectories will be used in our analytical channel model, which will produce the complex channel gain. And using complex channel gain, we are able to compute a spectrogram or Micro-Doppler shift or Micro-Doppler spectrum. And then this will then produce us to compute mean Doppler shift. So in here, as you see the figures, we have a signal on the left side from the real world measurement. And on the right side, spectrogram is obtained from the simulation model. So we can see that there are very much close relationship and patterns. And on the further right side, we can see the simulation model with the dotted red lines and measured data, which also reveals the quite good fitting in terms of the data. So how we basically build our channel model, analytical model. So we start first designing geometrical representation of our model. So first we will consider our environment, where in our environment we may have fixed objects or fixed scatters. And then we have a position of our antennas, AT, position of our receiver antennas, XR, YR, ZR, position of our transmit antennas, XT, YT, ZT, and then we have position of the person, or we can say in this case, person has multiple body parts, and then we have multiple moving scatterers or multiple moving points, if we can say. And then after building this geometrical representation, we will derive Euclidean distance from our transmit antenna to the receiver scatterer, which is moving scatterer. And then this impinged signal on the moving body will be scattered and received at the receiver antenna. So in this case, we will analyze the signal received at the receiver antenna. And we may, at the same time, may receive the signals scattered from the fixed objects in the environment. So, for example, from SFK. It can be a chair, desk, it can be a wall, it can be a window, if it is indoor environment. And this in the table, we can see parameters with respect to the position of our antennas, position of our fixed and moving objects, and the distances as well. So once we know the distances, then we can, before computing distances, we will obtain these trajectories. As we can see, X displacement, these are time variant, Y displacement, and Z displacement. And this displacement will allow us to compute Euclidean distances, these Ds, between the transmitter and the moving object and the moving object and the receiver antennas. And these distances can facilitate to generating our channel model. And here trajectories corresponding to the head, chest, and hips selectively. So we have 3 moving points corresponding to the person. And when we obtain our trajectories, we can compute distances as follows, and the propagation delays, taus, between the transmitter antenna and the moving objects, and the moving object receiver antennas. And then we can compute our time variant channel transfer function, which is the sum of moving channel transfer function and fixed channel transfer function, where we have K fixed scatterers, where we have N moving scatterers. And then we have complex our time variant path gain, which is dependent on the radar parameters and also depends on the distance functions. After computing transfer function, then we'll obtain our complex channel gain by using following equations, and applying inverse Fourier transform, we'll obtain our channel impulse response for identifying for computing short-time Fourier transform. And this short-time Fourier transform will facilitate to generate the spectrograms for that particular activities. And using the spectrogram, we can also obtain time variant mean Doppler shift as statistical properties of the underlying signal propagation. Let me now discuss a little bit the experiment outputs. So here we have a scenario where line of sight connection is assumed, so we have no other obstacles, and then person performs activities in front of radar. So here we have a radar, and these are the parameters used for this setup. So we have placed both transmit receiver antenna side by side, so they are located close to each other, and the frequency range is 24 gigahertz and bandwidth is 250 megahertz. So here we can see the activities. So as you see, this is for the real scenario, and this figure corresponds to the skeleton obtained from the optical motion capture system, and this avatar corresponds to the IMU-based motion capture system, which is Smart Suit Studio avatar. And we can see the exact motion for the corresponding activities. And here we have trajectories for the walking activities. So in this case, head, chest, back, and back right has been recorded for the references. And if we look to the output, so we see here that the spectrogram in this one, on the left side is the micro-Doppler signature corresponding to the walking scenario and for the radar, real data. And for the Qualisys mockup data, which is based on the trajectories, X, Y, Z, based on these trajectories, is produced micro-Doppler signature. And also at the same time, we have spectrogram or micro-Doppler signature corresponding to the data obtained from Rococo Smart Suite. So we see here very similar patterns. This is for the walking pattern, and we observe the close agreement between these spectrograms, and this will tell us the validity of the proposed approach and the framework. And finally, we can also see a very clear match in terms of mean Doppler shift. So if we look to the different scenarios, let's differentiate the scenarios so we can also consider experiment for sitting activities. So in this case, we have a person sitting. Also, you can see the hands on the knees. And of course, there is a little bit delay in terms of the time, but that's because of the different clock of the computer's recording. So we see different distinct trajectories for the sit-stand activities. And these trajectories will be used in our trajectory-driven channel model to produce the spectrograms as follows. So here we can see again, this is sit activities. So when we try to sit and then leaning the back, so we have a certain motion. So these spectrograms also corresponds to the radar data, to the Qualisys data, and to Rococo data. We see very similar patterns, and this data set basically will facilitate for us to generate multiple snapshots for training our future models. And now let's consider the scenario where we have no line of sight case, where the direct connection between the person is lost. For example, here, the receiver antenna is looking towards not the person, but to the window or to the wall, for example. And in this case, we have a smart suit, we have a radar setup, and then we have also the environment containing different materials like glass, wall, and etc. And here is the other model parameters used for this case. And here is the illustrative scenario for the case where we have a received signal not from the person, but from the wall scattering and from the window scattering. So in this case, we will see if we can get accurate or similar snapshot for the walking scenario, which facilitates to recognize the signal even though we don't see the target by the receiver antenna. And as you see here, we have very good agreement between the left side is our radar data, and the right side is the spectrogram corresponding to the motion capture from the Rococo Smart Suite. And this is for the signal coming scattered from the wall, not from the person. So how it works, it basically transmitted signal goes to the person, and from the person it reflects to the wall, and then the reflect signal will be received at the receiver antenna. So received signal at the receiver side will still carry on fingerprints corresponding to different activities. And similarly, we have this kind of activity for the window. So when we have received signal upcoming from the window cases. And now the question is why we need to consider using different body parts, not full body. So for example, from the real radar, it's difficult to identify, to classify which pattern corresponds to which body parts. And in this case, we see that we have right upper arm, right forearm, right hand, and then left hand, etc. But from the spectrogram, it's difficult to recognize if we do not process them individually or if we do not isolate them. So if we isolate them, then we can know, okay, a particular pattern corresponds to the movement of specific body parts. Why this is important? So this basically will facilitate to evaluate how the physiotherapy activities, for example, is performed. Is there any movement improvement? Is there any performance improvement? If there is any progress, for example, if we are dealing with the scenario to recognize Parkinson's cases, so we need to identify if there is any handshake, trembling, or speed variation. So these patterns are quite important to investigate. So for example, here you can see that this is correspond to the simulation model. We can see right arm down movement, and then here right arm up movement. So we have different snapshots. And in this case, this is the measured radar data. So it's quite not that clearly visible, but still we can, if we use the reference, we can identify those signals, snapshots. And this is we called our trajectory-driven model in this scenario is trajectory-informed model for emulating the signals. Okay, and so now simulated versus real data. So why we need to simulate? It's very challenging to involve the person in terms of the privacy issues, in terms of the GDPR regulations, to involve the real person in the activities. So we would like to generate these snapshots, what we have discussed, from using a simulation model. But we need to make sure that the simulation models are quite realistic and close to the real data. So in this regard, we have developed a simulation analytical model, as we have discussed here. So this analytical model and trajectory-driven model will facilitate to produce realistic snapshots, as we see here. It's realistic micro-Doppler signatures. So once we produce those signatures, then we can use these simulated RF signals to train our human activity recognition model, AI model. When we train this AI model, then we can use real data as a test samples to produce accurate classification, accurate recognition of a particular body signals. And you may say, okay, then we have to use this real person anyway to conduct the trajectories from the suit, from the motion capture, optical motion capture systems. But how it will work without involved any real person? Then we have to use a simulator animators or softwares. Like, for example, Mixamo Studio will allow us to generate, to scale the avatar or the person into different dimensions and in different scenarios. Or there is also a software called Motion Builder, will also allow us to generate the different types of characters. If we also consider the Unity Studio, this Unity Studio also facilitates to generate even the environments. So it will allow us to conduct the scalable and almost AI-ready data set for the human activity recognition could be generated, could be analyzed and used, which will facilitate not only waiting for conducting real-world measurement data, but to be sure, we first need to make it sure that our proposed simulation-based model is accurate and produces realistic data snapshots in this regard. Okay, so as a summary, so we have discussed what is the trajectory aware and non-stationary channel model, and that was in terms of very simple single input, single output scenarios, and it characterizes dynamic human activities based on the trajectories obtained from walking, sitting scenarios. And this includes time-varying matrix, including time-varying channel transfer functions, complex channel gain, and final spectrograms, which are micro-Doppler and mean Doppler shift statistics. And we have demonstrated the validation through the comparing the real-world radio frequency signals and the motion capture data from various experiments in different environments, actually. And this basically establishes a foundation for scalable synthetic RF HAR dataset, generating diverse human behaviors, diverse activities in different environments. And this facilitates robust AI model training across varied anthropometrics and motion patterns. And at the same time, it is hopefully will try to generalize the HAR performance when we will be used for example, for the smart home scenarios or home assisted cases. So as a future directions, this highlights the utility of simulation engines like Unity to generate customizable scenario-specific human trajectories for the precise RF modeling of precise radio frequency type realistic signal generations. And this promotes data efficient RF sensing by minimizing dependence on extensive experiments and measurements. And it enables the creation of synthetic behavior-rich datasets that support intelligent, personalized, and automation in the smart environments. It's very important also to consider the occlusions in different environments. And in smart environments where HAR also plays a very crucial role in personalized services, and this proposed model relevance lies in its capability to provide accurate real-time insights in human behavior. So these are all what I was planned for today, and thank you very much. If you have any questions, please, I welcome and to discuss.
Thank you, Dr. Nurilla. So it's really very fascinating and very interesting talk lectures. You have covered multiple important topics and try to compile and make a sense that how it can be useful for various kinds of applications, including medical applications and some other entertainment worlds. So really
Thank
great.
you.
So if any of you have any questions, so please feel free to ask directly to Nurilla. So yeah, Dr. Shahzad, please.
Hi, Dr. Nurilla. Thank you very much for this fascinating presentation, especially about this your work and how it can be applied in various different things. I have a quick question. Like you demonstrated like the applications, but has your work been adopted somewhere in healthcare or any study you have conducted in practical environments or in trials or something like that?
Not exactly in the health environment, but we have built the scenario. So for example, we were considering the smart home studio type environment, and then we try to replicate the certain activities. But to make sure that the proof of concept works, we have simplified the activities, as I have demonstrated. So walk, like for example, or sit, and we had also the fall detection, but it was not demonstrated here, but we were able to classify fall detection as well, because it has a very distinct pattern in our spectrogram.
Yeah, I think that will be a great work, because in the UK health sector, what I've noticed, especially in the care homes, they wanted to have these kind of systems which can alert them, because normally with the old people who lives in care homes, every time one person cannot be around with them.
No.
So I think this is really a great potential application, especially in the care home scenarios. Thank you very much.
Yeah, thank you very much for your question.
So as a follow-up, not follow-up really, but just related stuffs. I mean, is it the case that because you are capturing all these trajectories, and then, your spectrum keep changing, so does it mean that, if something happening or some changing happening, then early detection is actually even possible before this full spectrums appears? So that means the very subtle changes in the spectrums that we can analyze, and then some sort of, early fault detections even before they, become in trouble.
Yes. So basically, as I mentioned in Parkinson's cases, right? So we have some early detection possibilities, but for that will require very high frequency resolutions to be able to identify small movements. But that also will require a long-term monitoring to identify some anomalies in a person's activities. So this will definitely facilitate this prevention. For example, in terms of fault detection, the system can also recognize prevention and can alert that, okay, the motion is something is going not as it used to be, because it will be monitored various the long time period, and it can also detect anomalies. So this will facilitate and enable to detect earlier, so not on after the event happens. And this basically project has been conducted under the CareWell project, funded by the Norwegian government. And also we try to collaborate with the local commune, and also working on the future projects development. For example, not necessarily healthcare, but it also can be used for the human behavior analysis in terms of, let's say, in the office. So we work every day in the office, but we are not tracking how long we are sitting, how we use our posture. So this system will also indicate, okay, we have to now do some actions to try to change or correct our pose, our ergonomic position. And also, if we include this facial recognition, then this will also facilitate to how to continue the meetings with the colleagues. For example, if the suggested topic is key, or is it important, or should we switch the topic by investigating the people's behavior?
Great, thank you.
Yeah.
Is there anyone who would like to ask any questions, please? So I was wondering then, it's another, kind of aspect that while you were presenting, just taking a note a bit of it. So how about the multiple occupancy cases? I mean, how this signal will behave, in terms of multiple, or it's not relevant at all?
It is a good question. You mean in terms of multiple person existence?
Yeah, kind of, let's say.
Yes. We have done a little bit research on this, but it's again with respect to positioning. So localization should be in place. Then we have to consider the estimation, accurate localizing the person, and making the distinct differences. That's why I have highlighted the importance of a particular body parts. So if we are good enough in terms of classifying body parts, then we can also try to distinct the different persons with respect to their body shape, with respect to the dimensions.
Right.
And also, maybe it will require a multiple antenna scenarios.
Right. Makes sense. Yeah. So okay. So now this, another kind of very naive aspects that even though this might not be directly related. So for motion captures and those, optical, sensor placement, we are basically placing some, let's say, backscattery stuff to guide the signal. So in that case, is it easy that to manipulate the environment, or you folks did not even think those area because that might be a security or some other kind of aspects like
to manipulate environment, so it will be maybe relevant to the geometrical representation. So in a geometric representation, you have seen maybe some points, fixed scatter points. So if you consider not the point, but the area for the scatters, which means a certain area may have a multiple scatters, and then you can design your environment based on that. And then you can take an average on this.
right.
Yes.
Okay.
So
no problem, Hussein. So it's okay. Yeah, so we understand. So it's okay. So thank you for coming. Okay, so then I have last one things, the mean Doppler estimation, mean Doppler shift, or the quantifications that you are having. So how likely that we can actually do and capture those things with in real time using, let's say, some sort of deep learning stuffs, because, and why I'm saying, because the early days when we did signal processing stuff, so now almost those signal processing can be done easily. Just you feed the data and you get the, for mapping. So that's the thing. So I wonder that if that would be the case, that deep learning itself can give you indications of those Doppler shift stuffs based on just real-time data.
So since we have the trajectories and we can derive the velocity from the trajectories, or from the IMU sensor, they can produce the also the different parameters, let's say gyroscope, for example, right, or accelerometer. But at the end, we'll compute the velocity. So from the velocity, you can anyway need to derive the Doppler shift with respect to the starting position and ending position. And when you try to involve the mean deep learning, and then anyway, you have to need to have a data, labeled data. So you should have enough labeled data so you can then use the deep learning trained model to the unseen snapshots. You cannot generate mean Doppler shift, but usually you should have it already to either detect, classify correctly, or to train the model. So we cannot, but if you have some snapshots, then maybe you can try to forecast for the certain time after what will happen based on the trajectories.
Right. Thank you so much for taking time, and thank you for kindness for answering these things. So if anybody else have any questions, otherwise, we'll just, close this question answer segment. And of course, this recordings will be shared so they can also understand what's happening in this field. So with that, we will now go to the closing remarks for that. So if Nurilla, if you can stop sharing your screen, please.
Yeah. Thank you very much.
Just I'm sharing the screen. Aslam. So yeah, so on behalf of our small chapter for VTS Society here, would like to really thank you that you gave your time and sharing these things. So just as a token appreciation, this is what we can present to you, and I will basically email you these token certifications for your time and effort. And thank you once again for attending, all the attendees, and who I saw that there are many other registrants, but who could not participate now because of the Friday timeline, I guess. So, but I hope that they will be benefited from our recorded lectures one. So, if there is no other questions or something, then I believe that we can close our event, and then we can catch up at another times, and maybe in futures we'll also invite you again, and for your time and kindness to share your research and progress further.
Thank you very much. I would be very happy for the future participations, and appreciate for this opportunity. And I wish everyone for a nice weekend, and thanks a lot for the fantastic questions and the discussion.
Thank you so much. So have a great afternoon or evening and great weekend.
Thank you very much.
Bye-bye.
Bye.